Okay, hello. We're going to be looking at the practical for the bending moment apparatus within IC 0.19, the Heavy Structures Lab. The first thing that I would like you to do is look at your handout and just double check that you've read through the apparatus manual. You know, we're looking at HST 10, and whilst there might not be any risk using this apparatus, what I'm asking is that you at least wear a lab coat and eye protection for just in case there's anything else going on within the Heavy Structures Lab. So you're supposed to sign a declaration that you have reviewed the manuals for the bending moment and all other practicals, and that you've looked at the safety manual on the school website. Sign that, and then there'll be a tutor within the class flipping over to the actual bending moment apparatus. So you've got this within a hard copy within your handout, and there's also an electronic copy online for you to look at. And looking at the electronic copy, you know, you've got a little bit of guidance on safety and success in the laboratory. So read through. It talks about tolerances and potential issues there may be, and then we have here an image of the bending moment apparatus. As I've already covered a description of the apparatus in the previous video when I was in the laboratory, I'll skip most of this description. However, I will repeat some of the aspects considered necessary for the theory. What we have, there's a cantilever that's attached to the short beam. There's a strain gauge on the back of this cantilever, and as you twist this thumb screw clockwise, it will bend this cantilever, and the strain reading will be sent through the cable into the HDA device, which is here. So, you know, when we plug this in, just make sure that it's giving strain readings, otherwise you have to see one of the technicians as to why it's not giving any readings. You put the level either side, so you have the level resting on the short beam and just resting slightly onto the this edge of the long beam. Then you adjust the thumb screw, so the HDA device itself, if you unplug it and plug it in, it sets it off. It has a bit of a welcome screen, and then after this we are looking at HST 10. So hopefully it'll say HST 10. If it doesn't, then you have to click change, find HST 10, and then you'll be clicking select. Don't enter the configuration. There's two options. We can either plug it into a PC and take the readings off automatically, but what we'll be doing is that we'll be just taking off a local reading from the screen. So it's going to be local mode, and then we have to press tear. Now what tear does is that if we click on this green button here and keep our finger on, it will set the strain gauge to 0. So when our beam is at rest with no forces, our W is 0, so that will give us 0 all the way along. Now when we add 10 onto W1, we measure the strain reading, and I got a 192 value. Then it says remove the weight from W1, level the beam. So remove the weight, level the beam using the level again, press tear so it gets set back to 0, then add the 10 Newton weight to W2, and then read the strain reading, and I got 552. Do it again for W3, and I get 264. Now I didn't, for the sake of time, go through and put 20 newtons, but you're supposed to do that. So put 20 newtons on 1, 20 newtons on 2 and 3, and just record all of those readings also, but I'll just cross them out because I didn't do that in this video. Once I've done the first set of readings, we can move on to part 2, which is superposition. When I put 5 onto W2, then when I took everything off, again levelled the beam, tear, and then put on 10 on W1 and W3 and put 5 on W2, and I end up with a value of 718. Then part 3, I got 541 and 694. Now these are the strain values. What I need to do now is go back and work out what my practical force and practical bending moment is. But our bending force, you have a formula, E times strain times I over Ly. Our E is the Young's modulus of the material, the cantilever, so that's this cantilever here. The strain reading is the strain taken from the cantilever itself. I is the second moment of area of the cantilever, so we've got BD cubed over 12. In terms of the cantilever itself, it's this shape. Our B, we're told, is 9.5. Our D is 3.1. And our D over 2, so this is our Y value, is D over 2, so that's 3.1 divided by 2, so that's 1.55. And what we can do is we can put all of these values into our formula. So we have QC equals 70,000 newtons per millimetre squared. Our I value, where you put in 9.5 times by 3.1 cubed divided by 12, you get an I value of 23.585 multiplied by our strain. So what we have to do is divide our strain value by 1 times 10 to the 6, because mu is 1 times 10 to the minus 6. And then we have our L value is 47. The 47 is the distance from where the load is applied to where the strain gauge is on the actual cantilever. 47 and then times by R Y. That works out to be QC is 0.02266618 epsilon. So we'll be multiplying this constant by each of our strain values in order to get the bending force. So I'm going to go back to my tables and write in the bending force. So 192 times by the constant 0.02266618 gives us a bending force of 4.35. At 4.35 is at is the force here, and what we'll do after that is to work out the bending moment. So if this is the cantilever, we've got like 4.35, The cantilever length itself is 150. If we wanted to work out the bending moment for this 4.35, our bending moment is, again, the formulas on a couple of pages in, is our force 4.35, our bending force, or in this case 4.35, multiplied by distance. So it's moment is force times by distance, 4.35 multiplied by 150. So in terms of our bending moment, our force is always going to be changing, but we're always going to be multiplying by this 150 distance. 4.35 multiplied by 150, and we end up with 625 Newton millimeters. And we can work out our bending force for W2, 12.5, times by 150 gives us the 1875. W3 times by that constant gives us the bending force of 5.98, times by 150 gives us a bending of 897. So if we wanted to try and work out what the bending moment was at this point, what we need is the reactions. So if we took moment around A to find B, so sum of moments around A equals 0. So we got 10 times by that distance 100. That equals RB times by 900. So RB is 10 times 100 divided by 900. Therefore RB is 1.11 newtons. So if we wanted to work out what the bending moment was at this point, at 3 meters, we are 600 times by the reaction 1.11, and that gives us 667 Newton millimeters. And if we compare that to W1, the theoretical bending moment is 625. We've got 667 is the theory. If you do 625 divided by 667 to get a ratio, we have 0.94. So it's 90% of the theoretical, so it's quite close to the actual value. So W2 is 300 millimeters. If we take moments around A, what we would find is that RB is 3.33. And if you did your bending moment in the same way, bending moment at 3 meters at 300 millimeters. I don't know why I'm putting meters. 300 millimeters. It's 2,000 Newton millimeters. Put that theoretical value in. 2,000. Divide 1875 by 2,000 gives us 0.94. So again, it's 94% of the theoretical, so it's very close. You do exactly the same for the third location. So that's 600 millimeters in. 10 newtons. And then we got RB, you'll find is 6.667, and your bending moment at 300 millimeters in equals, so if we're considering this point here, we have minus 300 times by 10 plus RB times by 600. RB is 6.667. Therefore the bending moment is 1000 Newton millimeters. Put that in. One divided by the other. 90% accuracy. So you can write up the reasons why you think it may not be exact to the theory. So that's the first table done. Moving on to the second table. Again, the bending force is done exactly the same by multiplying by that constant. So 0 times by the constant is 0. 286 divided by that constant is 6.48. We have 16.27 for the readings that I have. And in terms of the bending moment, again multiply these by 150. So I have 0, 972, 2440.5. So let's look at the theory for this one. So looking at this beam, we were looking at applying 5 on W2, which is 300 in. Again, it's 900 long, so we've got A and B. We take sum of moments around A in order to find out what reaction B is. We've got 300 times by 5. Take away 900 times by RB. Our RB is 1.6 recurring. So if we looked at our moment, bending moment at 300 millimeters, we've got 1.6 recurring multiplied by this distance 600. That's 1000 newtons. So where you've got W2 there, our theory on bending moment in Newton millimeters is 1000 divided by one by the other, so we've got a ratio of 0.97, so it's 97% of it. Do exactly the same for the second case. So we have our supports, we have 10 on 1 and 3, and then on W2 we have 5. And when you start summing moments around A, considering 1 times 10, 3 times 5, and 600 times by 10, you'll find that RB equals 9.4 recurring. And then when you look at what your bending moment is at this point, your bending moment at 300 in works out as 2666.7. So we'll write that in here. One divided by the other, we've got 0.91. So So 91 and 97% accuracy. So part 3, we've got our forces, slightly different location, but in terms of our bending force, we've got 0 times by that factor gives us 0. 541 multiplied by that factor is 12.26. 694 times by the factor is 15.72. Multiply these by 150, we get 0 bending moment. 1839, we get 2358. So that's our practical bending moment. For our theoretical, and we'll also be looking at the ratio. What we can do is that we can draw out this scenario, so 5 and 12. So we can take moments around A to try and find out what RB is. In the end, RB so it's 1 times by 5, you've got your 500 times by 12 divided by your 9. I think it's 100, 500 and divided by 900. I'll just took the zeros out, they all cancel out. That gives us 7.2 newtons. That's what RB is. So we tried to work out what the moments were at 300, bending moment at 300. You've got this 12 times by 200. Then you've got 7.2 times by that distance, which is 600, and all of that comes to 1933. So 1933 is my theoretical for that scenario. 1 divided by the other gives me a ratio of 0.95. So we have 3920. 1 divided by the other, it's quite a big ratio. It's only 60% of the theoretical, so we really need to comment on what went wrong with the strain reading there, because our bending force and bending moment is very low compared to the theoretical. So this will help you in your understanding of theory versus the practical for beams and bending moment. All the bending moments were taken at this point 300 in. So work through it if you have time. Double check that you haven't got to do this as part of your assessment, and just be aware of the practical for just in case there is a question within the exam.